Welcome to our feedback project presentation on driverless cars. I'm Brennan.
I'm Jordan.
I'm Daniel.
This video will cover the development of a feedback control system for a driverless car, which will allow the car to adjust velocity and following distance with other cars in front of it.
Passenger vehicles today have several flaws and inefficiencies that could be improved. Since they are controlled by people, the chance for a collision with other vehicles is high. People can be distracted while driving by other passengers, electronic devices, fatigue, and other factors. Due to this control relationship between people and vehicles, collisions occur when these distractions prevent the driver from controlling the speed of the vehicle properly to avoid collisions with the car in front of it. There are systems in current vehicles which are designed to prevent collision, such as steering and brakes, but due to the reliance on the input from the driver, they can be ineffective.
By making the car driverless, the need for driver input is eliminated, and the risk of collision is reduced. Since the car will be taking in its own data about the vehicle in front of it, there is no element of distraction. The goal of this project is to determine a system to effectively collect data about the velocity of the car in front and relay this information to other systems within the vehicle which control the car and prevent running the car into the front. The driverless car needs to read the velocity of the car in front of it and adjust its velocity in order to maintain a safe following distance.
In order to quantify our system, the following units will be used. The velocity will be measured in meters per second. The distance will be measured in meters. We will examine the feedback loop of the car on the highway, and we will use the rise time, steady state error, and percent overshoot to examine the effects on the system. As a preliminary estimation, based on the predictions and behaviors of the car, our goals are 6 seconds rise time, 0% overshoot, and a steady state error of less than 2%.
The open loop system will have two main components, the controller C of S and the plant P of S. The plant is what happens to the car naturally if nothing were to interfere. This includes the mass of the car and the damping from the friction with the ground and air resistance. The controller is what the control box can change. The engine force will act on the mass of the car, and in a feedback loop, the brakes will slow the car to an appropriate speed to maintain the safe distance. The output will be the velocity of the car, and the input will be the force on the car from the engine. The brakes will be used in the feedback loop to keep the car going at a speed to maintain a constant speed that the user or a different computer system can adjust. Upon the simplification of the loop, you end with the transfer function on the right. After plugging everything in and simplifying, you get the function shown at the bottom.
Since we would want a response that isn't too fast or slow, the plant dynamics and response seem adequate. When braking, the response would have to be steady and not sudden that would affect the user negatively. The parameters we chose in order to perform the analysis were a target speed of 20 meters per second, a damping coefficient of 200 newtons, and a mass of the car of 2,000 kilograms. The plant is bounded input, bounded output stable on its own. The stability is proved by calculating the transfer function with Routh-Hurwitz criterion.
In order to control this feedback system, a proportional integral, or PI controller was used. This type of control uses two gains, Ki and Kd, to control the system. After some iteration, we found the appropriate parameters and modeled CS. Simplifying this system gives us the final transfer function shown.
Our three goals we defined in the setting of the problem, rise time, percent overshoot, and steady state error, were all met by our design. Our rise time was 3.96 seconds, which is in line with the power capabilities of most cars. This rise time makes sure the car is not reaching its final velocity too quickly or too slowly. The percent overshoot for our final design was 0. This is important because we felt like it would be dangerous going faster than the input, even if it were for a short time. Finally, the steady state error was 0.26%, which is well within our bounds. This is good because it means we get very close to the input speed.
To verify our results, we used MATLAB and Simulink to plot our step response, root locus, and photo diagram. You can see from our step response that the amplitude does not go past 20, which matches our target speed of 20 meters per second. The row locus plot shows the path of the roots as k is varied and gives the location of the closed loop holes as the gain is varied.
For the robustness analysis, we decided to look at the maximum time delay allowed in our system. When analyzing the Bode plot, our phase margin was found to be 0 at a frequency of 0 radians per second. This means the maximum time delay allowed in our system is 0 seconds.
In summary, the design of the system we chose for the driverless car works as intended and performs within the bounds and capabilities of most cars. The feedback control system meets all of our specifications and would help to eliminate accidents caused by distracted driving.